All right. First I have to share my screen. All right, here we are. So, welcome to pre-calculus. It's been a long summer, hasn't it? So yes, we'll be meeting. This class meets online every Wednesday at 8 o'clock. And let's see, we've got 19 people here. Now, I did send out the invitations yesterday. That's what I'll be doing throughout the course. My goal is always to have those sent out within, let's say, a day or so of the actual class. Um, I'll try very hard not to forget, but if you see that you do have one, you can go ahead and send me an email and say, hey, wait a minute, where's my invitation? Because it's possible that somehow it got into your junk box or possibly I've forgotten, but either way, it's okay. You can write back to me. And now, if you noticed, you did receive that invitation from my Gmail account. And that's just because it's easier to send out group emails from Gmail than it is from the purchase accounts. So that's why that happens. So yeah, here it is. This is my account. And so let's see, somewhere along here, I have sent you the invitations. There it is. Oh, sorry. There's always a few typos. Don't worry about that. So anyway, so going forward though, you can always contact me at either of two different email addresses. Let me just write them down for you right now. The one that you received your invitation from, that's draa2012@gmail.com. And then my purchase account is, of course, my name plus purchase. So if you're going to write to me, probably you should write to the purchase account, only because I do get a ton of emails in my personal account. And, there's always a risk that I might not see your message. If you send it to my purchase account, I have a lot fewer messages there, and that increases the likelihood that I'll see it. In the future, when we start having assignments, you'll be able to email your work to either one of these. When that happens, we have to be careful because often there are space issues with the files that we'll be using. But in the meantime, just be aware that there are always two emails for you to choose from. And again, I'll be sending the invitations from this one just because it's more convenient. Okay, in other words, it's easier with Gmail to send a bulk email with all the names on it. All right, now here's what we should do first. Let's go to Moodle and see what's there waiting for us.
Nothing.
Purchase Moodle. Everything in this class will be posted on Moodle. And so already, yeah, they changed this on us, didn't they? The links are in a different spot than they were in the spring, so you'll have to get used to that. So let's log into Moodle, and we'll see under pre-calc, there's a syllabus. Okay, there's also the first chapter of the book, and we also have already some practice problems. Now, these practice problems are meant for just getting some experience with these types of problems. These are not meant to be collected or graded. Instead, we will work on these as we go along just to make sure that we understand the concepts that are being presented. Later on, when it comes time to have exams, there will be actual more practice problems. But again, they won't be collected. The goal there is simply to get you as much practice as possible. So why don't we take a quick look at the syllabus, where all of these details are covered. So you could see here, we've got all the course information. We've got my information. Now, here's an interesting twist. It turns out that the book that we're using is actually not only free, but it's actually online. It's made by this organization called OpenStax, which has other math books available as well, if you want to check them out. So what you're going to do to find the book is go to HTTPS OpenStax with an X. Don't forget about that little twist. And let's see, where are the books? Okay. Oh, here it is. Subjects, math. And yes, there you go. You've got all the calculus books, you've got algebra, and the one we're using, of course, is pre-calc right here. It's a pretty large book, but you can download it and have a copy on your hard drive, so you don't have to keep coming back and reopening this website every time you want to use it. And it's a very good book, but again, the fact that it's free is really a very nice feature because, as you know, textbooks are just unbelievably expensive in this day and age. And this is potentially saving you maybe even a couple of $100s. So I like this book. So this is why we're using it. It's very well written, but also it's just available for free. Now, I don't know how these people make their money, but if you feel like you want to go ahead and review some of these other books, there they are. They're all free. So this is our book. Okay. Now, calculators. Now, you don't, this is not the kind of class where you really have to have a calculator, although it certainly would help. Most likely, you should probably end up using a scientific calculator, like the Texas Instruments 83 or 84. There's a very decent chance you've used that one in high school anyway, and you may already own a copy of one. If not, you can certainly use other calculators. The TI 83 and 84 does have some rudimentary capabilities for doing some of the topics that we'll be covering, which is kind of nice, but it's complicated to learn. As far as just straight ahead calculations are concerned, like, for example, dividing numbers or multiplying numbers, you can use any calculator you like. The Texas Instruments Business Analyst 2 Plus is very helpful for financial and business applications, but it's also a very powerful calculator. And there's another calculator that you all have access to. Let me just quickly show it to you. Hold on one second. Okay. Why, there it is. Let's see if I can show this to you without any glare here. See that right there, although it's backwards, it says calculator. Now, if you click it on, you'll see, well, it's this very basic calculator, which is not going to be all that helpful. But if you turn it on its side, you'll discover that, wow, this is a full-blown scientific calculator. It has everything that you might need, even for a class like this. It's amazing. And it's free. It's right there on your iPhone, which I know you all have one. If you have a different kind of phone, like an Android, let's say, most likely it also has something like this. I don't know anything about that, but yes. So in case you do need a calculator and you don't have one right there with you, just remember this app, as long as you turn it on and turn it on its side, it's now a very powerful scientific calculator. You just have to get used to it. Every calculator is slightly different. They all have their own little quirks. So you just have to get used to the way this one is set up, but it has everything that you need. All right, excellent. Now, then the rest of the syllabus discusses the chapters we'll be covering and the exams. Now, as far as grades go, because of this situation, being an online class, what we're going to do is simply have 3 exams, 2 midterms and a final, which you can do at home and send the results back to me. Typically in the past, we've had students take pictures with their cell phones and email them back to me. And that works well as long as you're careful to make sure that everything is legible. Okay, the phones are very powerful, but you have to be careful when you're taking pictures of documents. Now, having said that, there do exist some scanning software that you can buy for these iPhones. Let's say, oh, I've got one on here somewhere. Oh, here it is, Genius Scan. It's not the only, oh, wait a minute, what happened there? Okay, now it's backwards, but you can see that it says Genius Scan. It is basically a portable scanner. What it does for you is it just improves the quality. If you use the scanner, it turns it into a PDF format, which you can then email back to me. And I'm not saying you have to do that, but it does make it a little easier to read it. And so there's all kinds of tools available. Or if you actually have a printer in your house, most printers do have a scanner built into them, and you can just scan them, and that will turn them into PDF files, which can then be directly emailed to me. So anyway, no matter how you choose to do this, you'll be able to do your work at home and then email it back to me. It's not something that we can realistically do online, or at least the capability exists, but I don't think we have it at purchase. I've asked about it, and nobody seemed to know anything about it. So I'm just, you know, you can scan documents. Oh, really? You see, technology is not really my thing. So if you have excellent ideas like that, you can feel free to share it with me in the group, because I am the last person in the world who's going to find out about these things. In fact, I only know about Genius Scan because I asked my last class in the spring, and they were the ones who told me about it. So yes, anytime you realize that you have some useful knowledge about technology that I might find beneficial, you can just go right ahead and put it in the chat box. I will be very happy to have it, because I'm at least 10 years behind the technology curve, probably more. I'm trying to catch up, but it's not easy. So yeah, and then in my other class, people were sending me messages that had those little abbreviations in them, and I had to tell them, no, I don't know those abbreviations, so don't use them. Or the little faces, anything along those lines. You have to send me actual English words, otherwise I won't get it. But anyway, so I'll have just the 3 exams, but like I said, we will be doing a lot of practice problems though, because this is the kind of class where you have to practice. You just do. It's like learning the piano. You can't learn the piano just by reading a book. You've got to practice. So we'll get a lot of practice done. And by the time we're done, you should be fine. And so other than that, now, the one thing I do want to mention is this: if you, for some reason, can't attend the class in real time, all these sessions are being recorded. And now, unfortunately, Moodle is not really designed to hold a lot of large files. Videos do take up an awful lot of space, apparently. So I tried it in the past, and the school told me don't do that anymore, because Moodle isn't really meant for this kind of thing. So instead, what I do is when the recordings are ready, I put them on YouTube. Okay, so I've set up some YouTube. I have my account here. This is my channel. And so what you'll find when you go to my account here, I have a series of what are called playlists. And the reason for doing that is because I have a lot of videos here from past semesters that you don't want to have to, look through them all. So it isn't there yet, but there will be a separate playlist for our class. And it'll just say Math 1150 Fall 2021. And when you click it on, like, let's say it's not this one, but if it were, you'd see there's a whole list of videos for you to choose from, and you can feel free to either watch them, or you can download them, or do whatever you want. That way, if you miss class, at least you'll know exactly what we were doing. So the school kind of expects you to do one or the other. In other words, either be here in person or watch the videos, or some of both. You can certainly feel free to watch the videos, even if you were in class, just in case you missed something. You never know. So there they are. So you should have no trouble finding them. And, the YouTube, I've never run into any space problems with it, even though these videos are actually quite large. And it seems to work pretty well. The quality is pretty good. And what I find is very occasionally people who are not even going to purchase watch these videos, which surprised me a little bit, but it does happen. So I guess there's some value there, huh? All right. So just remember, it's just when you go to YouTube, just look for my name, and you should have no trouble finding it. Okay. So other than that, I think that's all we need to go over today before we start diving into the new material. Now, this is a very, very long class, as you know. So for sure, we'll have to have a break somewhere in the middle. Um, this is not meant to be a contest of endurance. Yeah, the math is wonderful and all, but you can only do so much at a time. So somewhere along the way, we'll have a break where you have time to go get something to eat or drink or whatever. But for today, what we'll do is we'll start with chapter 1. And the material in chapter 1, most likely a lot of this is review, but it's possibly been a long time since you saw any of this content. So, if it is review, that's nice. There's nothing wrong with a little review. If it's completely new, that's fine too. I know everybody in this class has not everybody has radically different backgrounds, but not everybody has the same background. Let's put it that way. Some of you are actually majoring in math, and some of you may not have had any math classes for years, and we'll have everything in between. But fairly soon, we'll all be together on the same page. And by the way, what comes after this class, if you are actually majoring in math, the next step after this is Calc 1. And if you do want to read ahead on that class, let's say during the Christmas break, you can go back to OpenStax and take a look at their calculus books. Okay, just in case you're interested. The last chapter that we'll be covering is essentially the bridge into calculus, where we introduce the topics that you'll be doing a lot of in Calc 1. Now, some of these topics are more abstract than others, and some of them are meant to be very useful, but I think they're all very interesting. Math is a very large subject. It covers a lot of different areas, but the purpose of this class is to give you a solid background that you can apply to many other areas of study. Like, for example, obviously, if you're a math major, but also if you're a computer science major, or if you're possibly an economics major, all of this will be extremely helpful to you in some form or other. Also, if you're interested in studying more math, another class you might want to consider is statistics. We actually will do a brief introduction to statistics towards the end of the course. The difference between statistics and, let's say, calculus is that the statistics is intended to help us explain what's happening in the real world, whereas the calculus is really, at least it was originally intended, to help us understand the laws of physics. In other words, you may not realize it, but Isaac Newton actually invented calculus just so that he could explain his laws of motion. And so, the idea is that he has this great scientific theory and there's no math to prove it. So he said, well, what the heck, I'll just invent the math that I need to show everybody what I'm talking about with physics. So they're two very different disciplines. So anyway, enough said. Why don't we go ahead and start looking at our first chapter, which is a review of functions. Now, everything in calculus ultimately is based on functions. So we need to understand what they are and what their properties are. And so as we go along, just remember everything that we're seeing here, the class is being recorded, and the notes are on the Moodle. If I write anything, now I do have this wonderful tablet, which I will be using periodically. And what it does is it lets me actually write on the screen. So if I suddenly realize that, let me add some more notes here to clarify what we're doing. I can physically handwrite it in here, and then I can save the recording, the slide rather, with these handwritten notes on it. And so I will do that as well. So you'll have not only the slides, but the slides with my handwritten notes. So that way you don't ever miss anything. And if you do, you can go back and check them out on Moodle, or in the case of the recording, on YouTube. All right, so you don't have to feel like you must sit there and write down every single word that I'm saying, because it'll be available to you. And it's really more important to understand than to just write. Okay. It's easy to get into the habit of just write. But, ultimately what we're trying to do is understand this stuff. All right. So why don't we start at the beginning here with functions. So we're going to be looking at different kinds of functions. So we're going to start out with a very basic concept. A function is actually a special case of what we call a relation. And a relation itself is nothing but a set of ordered pairs. Okay, so you might recall from your math travels that we can illustrate ordered pairs on the so-called XY coordinate system. Okay, for example, we have X and Y. And every point is uniquely identified by an ordered pair. This could be, for example, let's say this is 3 and this is 5. So this is the ordered pair 3, 5. And of course, the first element is the X coordinate. The second element is the Y coordinate. So let's say over here we have the point let's say this is 7 and this is -4. This is the ordered pair -4, 7. Okay, so whenever you see ordered pairs, they represent the relationship, a relation actually. So you've got the X coordinate and the Y coordinate, and that uniquely identifies this point. Now, also, you might recall that if you draw this thing out again, the different regions of this graph are identified with what we call quadrants. Okay, you might remember this from high school. And they don't go in the order you might expect. The upper right-hand corner, we have the so-called first quadrant. Then we go to the left, we have the second quadrant. Then down here is the third quadrant, and down here is the fourth quadrant. Now, I do not know where the names came from, but this is how they're referred to. And what's important is that in the first quadrant, X and Y are both positive. In the second quadrant, the X's are negative while the Y's are positive. In the third quadrant, both are negative, and in the fourth quadrant, the Y's are negative, but the X's are positive. For many real-world applications, we restrict our attention to the first quadrant because we may need to have just positive numbers. But in general, we can use all 4 of them. Now, interestingly enough, here's a little historical side note. This graph, the XY coordinate system, was invented by a very well-known individual from 17th century France. He was a mathematician, a philosopher, a theologian. His name was René Descartes. And these points on the graph are known as Cartesian coordinates after him. So each ordered pair is referred to as a Cartesian coordinate. So now, of course, you don't have to remember this. I mean, this is just, I mean, it's fun to know these things, but, you know, I'm not going to test you on these definitions. But yes, this comes to us from Descartes. What matters to us is that you understand how these ordered pairs work. All right, so therefore, what we're going to do is define the concept of the relation in terms of ordered pairs. Now, the ordered pairs themselves are gathered together into a set. And now there's no necessary, there's no rules about relations. Anything goes with relations. We'll see in a few minutes that that's not true with functions. But with a relation, it's really just a collection of these ordered pairs. And that forms the foundation for what we mean by a function. Okay, so let me just quickly go back to the first slide. Okay. And so this is an example of a relation. And literally, as you can see, all it is a set of ordered pairs. And by the way, you might recall that when we use these symbols, These are formerly known as braces. And when you see braces, this means that this is a set. Now, later on in the course, we'll be doing a lot of set theory, but you might recall from your travels that a set is simply a collection of objects. They could be numbers, but they don't have to be. And the order in which we list them does not matter. Although we typically try to keep them in some logical order, it doesn't make any actual difference. So here we have a set that contains 3 ordered pairs, and we call this a relation. Okay, relation. Notice how it's not relationship. That's different. This is a relation. And it just indicates that there's some connection between these points. We don't know what it is just yet, but like it could, like in a non-numerical sense, be a group of husbands and wives, for example. Or it could be a group of people and cars. You know, it could be almost anything you could imagine. Or people and their ages. So it's really just the idea of 2 things that belong together somehow. All right, now let's use this as an example. This is our relation. And you can draw this out if you choose to do so. It may not have any particular pattern to it. For example, let's say this is 1, 3, 2, 5 would be up here somewhere, and 3, 7 would be up here somewhere. And we call that a relation. Now, we're not going to use a lot of relations in this class. We're going to use functions, but functions are ultimately defined in terms of relations. So this is why we have to go over this first. All right, now on the next slide, you're going to see a word that you have seen many times before, I'm guessing, but it's probably been a while. Okay, it's like an old friend is coming back to visit. Are we ready to revisit our old friend? Okay, that word, that friend is domain. Remember domain? Domain is the set that consists of the x coordinates in these ordered pairs. So if you notice, the domain of this relation is very simply the set that contains 1, 2, and 3, because those are the x coordinates. And that's all there is to it. Now, if there's a name for the x values, there must also be a name for the y values. Let's see if you remember. Let's see. Let's see if anybody remembers what would be the word or the name associated with the y value. There it is, the range, exactly. That's right, very good. So the word range indicates the y values. Okay, so you have a domain and you have a range. And in fact, we're going to spend a lot of time analyzing the domains and ranges of functions. It's very important. Now, with all this in place, we can now formally define what we mean by a function. With a function, what happens is it's a special type of relation where every single value in the domain is associated with a single value in the range. Now, we'll explain this in a minute. It's very abstract the way it's described, but you'll see what I mean in a few minutes. Now, it's important, though, that every element in the domain must be associated with a single value in the range. You can't have, for example, a single element in the domain associated with two or more values in the range. But you also can't have an element in the domain not associated with any element in the range. It has to be one-to-one. Each element in the domain gets one element in the range. So one-to-one. Now, let's look at a graph of this. This is a fairly typical way we represent sets and define functions on them. So the way we've got this set up, we have X and Y are two sets of numbers. F is a function. These values represent the domain, and these represent the range. So this graph is just a different way of writing out 1, 5, 2, 15, and 3, 10. But the graph makes it easy to see visually that every element in the domain is associated with exactly one element in the range. And therefore, this is a function. Okay, F for function. And that's really all that it means. Whatever we have in set X, each element is associated with a unique element of Y. And that's what it means to be a function. It's also, by the way, it's also a relation, but it's a special kind of relation. Now, let's look at this example. Now, this is, again, this is a relation. In fact, it's the relation 1, 5, 1, 10, 2, 15, and 3, 10. But does this qualify as a function? The answer is no. Oh, somebody's got it. Yes, it can't be a function. Exactly. And the reason is because 1 is associated with both 5 and 10. In fact, you can see in these two ordered pairs, we've got 1 associated with both 5 and 10. So this is not a function. It is a relation, but it is not a function. Okay, so bad luck. This one is not a function. And what the direct practical relevance of this is that there's a lot of operations, let's say, that we cannot perform on this relation that we could perform on a function. Okay, now on the other hand, what about this one? This is the relation 2, 15, 3, 10. Is this one a function? No, because 1 is not associated with any element in the range. Okay, or I guess what I should say is Y. We technically shouldn't call it a range if it's not a function. So in set Y. Okay, so that rules out this one. All right, so let's just quickly look at them all again. Okay, the first one is yes, because each element of X is associated with Y. Some element, it has to be one, exactly one. This one does not count because one is associated with two elements in Y. And this one does not count because one is not associated with any elements in Y. Okay. Now, here's an interesting application. This relation is also a function, in spite of the fact that the first value is not a number. What if you walk into a Dunkin' Donuts and they say, all right, here's the price list. Small coffee is $1.50. Medium coffee is $2.25. A large is $2.75. If you were to draw this out, you would see, I mean, you can probably see it from here. Each element, let's say this is our X. Let's do this. Small, medium. I'll have to abbreviate that one. Okay. And so we'll draw the picture. Yeah, this is. And so therefore, this is a function. Some function F. The coffee pricing function, we'll call it. Yes, and so because the two sets X and Y are not required to contain numbers, although certainly that's usually the case. It would be pretty ridiculous if this wasn't true. Imagine if you walked in the door and they said, well, the medium coffee is either $2.25 or $2.75. Oops, well, that would be a mess. So no, this is a function now. So what we can do then is note here, if you notice that the size of the coffee determines the price, it's not the other way around. So what we can do is write the following. Price is a function of size. So X, the size is what's determining the price. So we'll think of price as Y and S, the size is X, which we did back here. The prices are Y's, the sizes are the X's. So you might recognize this expression. You've seen this before. Y is a function of X. And that simply means the size determines the price, not the other way around. And furthermore, you might recognize these definitions. We say that X is the independent variable and Y is the dependent variable. Okay. Yes. Now, I'm sure you've run into this before, but maybe it's been a while. So the X is independent because it determines the value of Y. The size determines the price. And you can come up with all kinds of other examples too. For example, your height determines your weight. All right. In that case, if you were studying the relationship between people's heights and weights, you would find that the height is what determines the weight, okay? Normally, the taller you are, the heavier you'll probably be. So therefore, height would be considered an independent variable. And here we have the dependent variable. Okay, so I put this together in a little chart. Rather than drawing it as with circles, in a case like this, it might make more sense to make it as a chart, but you get the idea. These are the X's and these are the Y's. And you don't need the arrows in this case. It's pretty clear that each size is associated uniquely with one price. Now, before we go to the next example, I just want to draw one more picture. I think this is an important case that I want you to see. Suppose we had something like this. I don't believe we've considered this case just yet, so let me throw this one out there. It's not what I wanted. Is this one a function? The answer is yes. You might be surprised to learn that. You might say, well, wait a minute, there's 2 going to 5. That actually does not matter. What matters is that each X is associated with one unique Y. It's possible for more than one X to be associated with the same Y, and that still qualifies as a function. The key detail is that each X goes with exactly one Y, even if 2 of them are the same. Now, let's go back for a second. Let's distinguish that from this case. You see here, that was not true. One is being associated with 2 different Y's. That's why this one doesn't work. The problem here is that one of the X's, the one is associated with 2 different Y's. That's not allowed, but this case is allowed, okay? It's all that matters is that each X is associated with exactly one Y. So it might not look like it, but it is.
Yeah, can I ask a question?
Yes, go ahead.
Can you go back to the other slide that you just showed?
Yes. Let me scroll that up. And
the one that wasn't a function one.
Right. This one is not.
Yeah. So like I don't understand how this can't be a it's like if X is on horizontal and Y is vertical, can't you just so wouldn't wouldn't the 10 be on top of the 5? That's what the 1 is both connected to. Do you know what I mean?
Yes, you can draw this, but it's not. You'll see later on. This is not a function because each X has to be associated with exactly one Y. Even though, yes, you could draw a picture of this on the XY coordinate system, it does not qualify. In fact, we're going to see later on that when you have something like this, X is 1 and Y is both 5 and 10. A vertical line like this does not qualify as a function. In fact, you can tell it's not a function if it's a vertical line because you can see the same X has both Y's associated with it.
Gotcha.
So that means this is out. Now, to put it in more concrete terms, what if the box on the left, let me make, this might make a little bit more sense. Because in terms of actual real world applications, what's going on here? Suppose you had, instead of numbers, you have, let's just keep this simple. So here we have names and we have colleges. Is it possible for John to both simultaneously attend SUNY Purchase and UCLA? Well, not really. I mean, I guess in theory, he could take an online course at UCLA, but I mean, the idea here is that it's not a function because he's going to be associated with he should only be associated with one school. Or, you know what, maybe even a better example would be birthdays. Let me change this a little bit. We have John and Mary. And let's say the two dates here are January 30th, and this is April 20th. Can John have a birthday of both January 30 and April the 20th? No. So therefore, this is not a function. Okay, so these are obviously people, and these are birthdays. So therefore, I mean, the relationship between people and birthdays is a function in the real world because each person has exactly one birthday. But what we have here, this graph here, is not a function because John is associated with two different birthdays. Okay, so anyway, so let's come back down here. In fact, that was the next example, so that's why I used it. We've got people and we have birthdays. Is this a function? Well, we've already seen that it is. Even though you notice two different people have the same birthday, it's still a function because each person has exactly one birthday. So the answer is yes. But of course, obviously, different people can have the same birthdays, but each person has to have exactly one birthday. So all of the X's, these are the X's, by the way, and these are the Y's. Each X has associated with it exactly one Y. But yet, yes, like I said, we can have repetitions like we did here. Like if these were names and birthdays, you could see multiple people have the same birthday. But as long as each person has exactly one birthday, we're all set. Okay, how about this one? Now, I find that it's easier to do this with the pictures. Let's quickly put together a picture. So in the X's, we have 1, 2, and 3. And for the Y's, we have 1, 2, 3, and 5. So the first one is we have 1, 1. We have 1, 2. Uh-oh. Looks like we're in trouble. Why are we in trouble?
One of them doesn't have an X, I think. That could. Oh, no. One has two Y's.
Has two. That's what the holdup is. One is associated with two different values of Y, and therefore the answer is no. Okay, again, it would be equivalent to the same person having two different birthdays. It's not, this is not a function. Oh, I did draw the picture. There it is. Okay, so this is our, I mean, so right now, I'm hoping that everybody gets a function is a relationship, but a relation doesn't have to be a function. So in other words, in fact, if you wanted to use set theory, let me just throw this out here, just to see if this makes sense to you. Man, this thing is a pain. It really gets in the way. So each function is a relation, but each relation is not necessarily a function. So if you wanted to draw a picture of this, if you could visualize all the functions and all the relations, this is the set of all relationships, sorry, relations. And this is the set of all functions. So we say that the set of functions is what we'll call a subset of the set of relations. Meaning it's completely contained within the set of relations. It would be like, let's do something over here so you can see something less abstract. So among all purchase students, some of them are math majors. And so the math majors represent what we'll call a subset of all the purchase students. Yeah, so we'll see set theory as we go. It gets sprinkled in here. Set theory is important. It's kind of a fundamental concept of virtually all areas of math. So we'll use it as we need it. But it's especially important in fields like computer science because computers actually work on sets of numbers. But anyway, so now the next thing we're going to do, now that we really understand what functions are, we're going to evaluate them. We're going to provide them with a value. So in other words, we're going to no longer use ordered pairs. We're going to write out functions in an algebraic form, which makes it possible to evaluate them. In other words, to associate numerical values with them. Here's a quick example. What if it turns out that I can create a function which tells me how much it costs to buy gas? It's a very simple function. Look how easy that is. For every gallon of gas that I buy, I pay another $3.65. And I just want to remind everybody that I could just as easily have written this as y equals 365x, but there's a specific reason for doing it this way. I want to know how much it costs to buy 10 gallons of gas. What do? Oh, here we go. I simply replace all the x's with a 10. And I discover that in this extremely simple example, 10 gallons of gas will cost me $36.50. So that is our first example of evaluating a function. So it's a pretty straightforward idea. It can get very complicated, but the concept is very simple. So let's take a more complicated version, which, by the way, Just to test your memories, when you have a function with a square term in it, it has a special name. Does anyone know what that name is? Okay, where's the chat room? Quadratic, exactly. So don't worry, we'll get back to this later on. This is a quadratic equation. Ooh, doesn't that sound impressive? Quadratic. Because it has a squared term. I want to know, by the way, oh, you know what I almost forgot? There's a very useful tool on the internet that we can use to graph these functions so we can visualize what they look like. So I'm going to introduce you to a very cool website right now. And you may have seen this yourselves. It's called Symbolab. And what it lets you do is solve equations, but even more importantly, it lets you graph them. So I would like you to always be able to visualize what these functions look like. So here, for example, we're going to type, it will accept it as y equals, I don't know if it'll take the f of x notation, but x squared minus 3x plus 7. You'll hit the go button. Now, it's going to do a bunch of stuff, but I'm going to ask it to graph this. Graph. There we go. That's what it looks like. Now, this type of graph has a very special name. Does anyone remember what it is? It starts with a P. Parabola, that's correct. It is a parabola. Let me just double check and make sure I'm doing this right. Yes, that's pretty much what it looks like. Now, when x equals 7, let's say right about here, we want to know what y is equal to. How do we do that? We plug in a 7 wherever we see an x. Now, this is not a terribly complicated case. So just remember, replace all the x's with 7s. So we've got 7 squared minus 3 times 7 plus 7. And you can see that eventually works out to be 35. Oh, so this is fun. The definitions are always a little abstract, but the actual operations that we can perform are often very interesting. So if I wanted to know, like on this curve, when x is 7, what's the value of y? That turned out to be 35. Now, this could, for example, be a function from economics, where this tells me how much revenue I'll earn if I sell X units of this good. And according to what I'm seeing here, if I sell 7 units of this good, I will earn $35. Okay, that would be a classic example of this. Or it might mean that if I produce 7 units of this product, it will cost me $35 to make it. It could mean almost anything. Now, oh, and look at this. Now, what if I want to know the value of x when x equals a? I don't know why I would want to do that, but you can replace the x with an a, and then you have a more functional relationship. You may not. This may not be terribly helpful, but no matter what you replace x with, you'll have your answer. I guess in principle, I could put blue in there, but no, that wouldn't make a lot of sense. Okay, solving functions. Now, this is going to be something that will occupy a lot of our attention. Solving. Now, let's just say that we have this function. Now, once again, let's go to Symbolab for a minute and take a look. This one's slightly different. X squared minus x minus 12. Now, if you notice with this parabola, oh, whoops, sorry. Where is it? Aha. Now, unlike the previous parabola, here there are 2 points where this parabola crosses the horizontal axis. All right. And if you notice, Symbolab is actually telling us what those points are. -3, 0, +4, 0. So let me just see if I can draw a little picture here. This is what we mean by the solutions. Now, if you notice, when this function crosses the horizontal axis, x either has a value of -3 or 4. So we say that -3 and 4 are the solutions of this function. And sometimes I just want to mention, as is so often the case in math, there's multiple words that mean the same thing. Sometimes the word solutions is also referred to as roots. You may have heard it called that in the past. Solutions are roots. These are the points where y equals 0. In other words, where the graph crosses the horizontal axis. And if you notice, this happens twice. Because that we have a squared term in here, that ensures us that this function will cross the axis twice. So we don't even have to draw a picture. What we're trying to do is figure out, where did these come from? How do we know that the solutions are -3 and +4? What if you don't have Symbolab in front of you? I mean, it's so easy. Here we are, the 21st century. We're so spoiled by the technology. What if it's 100 years ago and you have to figure this out by hand? What would you do? Well, there's a couple of options here. And I'm sure you'll remember as we go along. So let me just throw in a new slide here for a second. 2 possible ways of solving a quadratic equation are, number one, something called factoring, and number 2, the quadratic formula. Oh, the good old quadratic formula. How long has it been? Again, it's like an old friend coming to visit, isn't it? It's like your friend from the 8th grade who moved away and now he's moving back into your town and you're so happy to see him. So we'll get to that in a few minutes. And by the way, all right, just for the fun of it, I'm going to help you remember it. Well, you probably still remember it. What does it look like? Oh, wait a minute. What comes next? Is this ringing a bell? Yes, it is. Somebody along the way made you memorize this, didn't they? Your 8th grade teacher said you must memorize this, and you were very unhappy at the time. Now you're happy because you have this useful tool at your fingertips. All right, so let's quickly review these. Yes, it's all coming back in a flood, isn't it? It's like you had this big door in your memory that was locked for many years and it's gotten all covered with cobwebs. And now you popped it open and all the memories are gushing back out at you now, aren't they? All right, so let's start with the factoring. Now, with factoring, what you're basically doing is you're taking this quadratic equation and you're breaking it down into two factors. These are referred to as factors. Each one of these, and by the way, M and N are just some constants which we are solving for, okay? They could be anything. And so this is referred to as a binomial expression. Why do you suppose it's called that? What is the key in that word that tells you? If you notice, there's two terms in here. Right there. So we're basically rewriting this as a product of two binomial expressions. The question is, how do we do this? Okay. All right, are we ready? I'll give you a minute. Okay, so here's what we're aiming to do. Oh, by the way, I almost forgot. Let me take a little detour here. I'm going to review with you one of the most interesting techniques you've ever learned, and it's called FOIL. FOIL. When was the last time you thought about FOIL? What does FOIL stand for? Who remembers?
Wait, isn't it an acronym or something?
Yes, it is. And what are those?
Isn't it like fractions? I think that's it, man.
Oh, you're getting
whoops.
a little rusty.
Someone already said it.
Inner and last.
That's right. So we're going to do one right now just to make sure you remember how this works, because you'll need it. I'm not just doing this for the fun of it, although we know that it's fun. That's understood. Okay, so this expression will give us a quadratic expression, but which one? Okay, so F is these two. I'll write it here. O is these two, which is 4x. I would be these two for inner, and last would be these two. So you see what I did here? I multiplied for F, x times x. F means the first term in each expression. O is the outer, meaning the first in the first expression and the last in the second one, which is x times 4. Inner is these two, minus 2 times x, and then last would be these two, negative 2 times 4. And now you just add them up. X squared, combine these two. So these are equal to each other. You can see that on the right-hand side, we have a quadratic expression. These would be considered to be the factors of this quadratic expression. So what's happening here is that with a FOIL, you're taking the factors and turning them back into a quadratic expression. Here, what we're trying to do is take the quadratic expression and figure out what the factors must be. Now, fortunately, the factors are unique. There's only one set of factors that will work here. But how do we identify them? Well, there's a few different ways you can do this, and you may have been taught a different approach. But I think what we're about to do here works pretty well. People have tried to show me these diagrams that they were taught in high school, and whatever works for you, just use it. Okay, but here's a possible way of doing this. Given that if you can write out the factors like this in a general form, there's two things that we know. Based on FOIL, remember what this term is. This is actually the sum of O and I. So -1 is the sum of O plus I. This -12 is the last. So what that implies is that the product, or sorry, the sum, M plus N, is going to give us -1. And it implies that M times N is going to give us the last. Okay, so in other words, one more thing. I just want to remind you too that when we write out these quadratic formulas or equations, the most general expression here is that you can write this as ax squared plus bx plus c. So this -1 here is b, and this -12 here is c. So in our case, the M plus N equals the B, or -1, and the M times N is the -12. Both of these things are true, and that's important because we now have, you can think of this as two equations two unknowns. Now, what you should probably do here is think of all the factors, as they're called, of -12, right? In other words, let's do this. M times N is -12. Now, how can we obtain -12? We could try 1 and -12, -1 and +12, 2, -6, -2 and 6, 3 and -4, -3 and 4. In other words, if I multiply any of these numbers together, I'll get -12. But we also know that M plus N is -1. And there's only one pair in here where that's true. If I add together these two, I'll end up with a sum of -1, as well as a product of -12. So what that implies is that my factors must be x plus 3 and x minus 4. And we can prove this by applying FOIL to these two values. F first would be, let me just erase this part. Yeah. Here's F. O, -4x, I, 3x, and last is -12. And when you add these together, you're going to get x squared minus x minus 12. There you go. So we must have done this correctly, because when you apply FOIL to those factors, you do find yourself with the original expression. Now, I don't know about you, but I found that to be kind of a headache. I'd rather just use the quadratic formula. It's so easy. The problem with factoring is that not only is it a clumsy process, but if you start getting very complicated expressions, it can really become a nightmare. This quadratic formula is so simple and it always works. So why don't we do that one right now? Okay, let's go back. And we'll do this again later on, don't worry. I just want to reintroduce it now because we need it. All right, so here we go. So if you remember, a quadratic expression or quadratic formula is written in general as ax squared plus bx plus c equals 0. In our case, a equals 1. It's the coefficient of x squared. B is -1 and C is -12. So once you, what you're basically going to do is plug that in to our quadratic formula. So we'll have minus, now you have to be super careful with the negatives. If you're going to make a mistake here, almost without fail, it has something to do with negatives. Okay. So here we have 1 plus 48. Wow. This is taking a while, isn't it? So then we can write this as all right. And that works out very nicely. You can see. Let me copy that here. Of course, that 1 plus and minus means 1 minus 7 over 2 and 1 plus 7 over 2. And that's what we got. Now, you might say to yourself, well, wait a minute. When we factored this thing out, we had x plus 3 and x minus 4, didn't we? But it turns out that if you set these equal to 0, the actual solutions, in other words, the points where the function crosses the horizontal axis, are actually -3 and +4. Okay, in fact, let's go back to Symbolab. -3, +4. That's what we're ultimately interested in, not so much the factors, but the solutions. So in other words, yeah, so here are these factors. I guess I forgot to do that here. The last step would have been to set these equal to 0. Because this is really what we're after, not the factors, but these solutions. These are the so-called solutions. But either way, you get the same result. But I really think the quadratic formula is the way to go. It's so much more straightforward. It just is. Now, how do we prove that this worked? Well, let's try this. Let's go get the formula again, the function, and plug those numbers in. Okay, in other words, let's do it up here. Here's our double check. Remember, originally we started out with x squared minus x minus 12 equals 0. Let's see if x equals -3 works. Well, that one works. On this side of the fence, what happens if x equals 4? Is that going to work? Why, yes, it does. So we must have found the correct solutions. So Symbolab did it correctly. And they gave us a graph to prove it. Wow. Now I did the same thing here in Excel. Excel is really not maybe the perfect package for these types of graphs, but you get it, you get the idea. Ooh, now don't you worry, we're going to get tons of practice with this stuff. It's not the case that we'll be just blowing through a ton of material. We're going to have multiple opportunities to practice what we're learning here. I'm hoping, though, that it's coming back to you fairly quickly. If you haven't seen it before, that you'll pick it up quickly. I do want to go back here for a second and introduce a couple of key terms, though, in case you've forgotten. You know, vocabulary is not the most important thing in the world here, but when you look at the quadratic formula, this expression by itself is known as the discriminant. Now, here's the big question. What happens if b squared minus 4ac is negative? What would that introduce a problem for us? What would happen? We'd have the square root of a negative number. Is that allowed?
Sort of.
Yes, sort of. What kind of number is that called?
An imaginary number.
That's right. So now we're not saying that we can't have that happen. If the square root all right, let's put it this way. The square root of a negative number is known as an imaginary number. You might recall that, for example, the square root of -1 is given the special name I. That's called an imaginary number. So if you do get that, then you're going to have imaginary solutions. Now, you might say, well, that's not possible, is it? Yes and no. It basically, you can't rule it out, okay? It is possible to happen, but I'll tell you what. That gives us a completely different set of numbers. Now, we will have imaginary numbers later on in the course. Not so much in the early chapters, but we will eventually encounter them. And this does show up a lot in certain disciplines like engineering. You can have imaginary numbers in your solutions, but they're very difficult to deal with, as you can imagine. So we'll try to avoid that for the time being. But I do want to give you a quick hint here as to how to recognize when this might happen. If you've got a parabola like this, okay, you notice how it crosses the horizontal axis. And let's say we'll call this just x1, x or y1. Then you're guaranteed to have real solutions. They may be messy numbers, but they're guaranteed to be real. What would be required to have complex or imaginary numbers? If the parabola doesn't reach the horizontal axis, then you're going to end up with imaginary solutions. Because if you notice, there's no place where y equals 0. Okay, so, and we'll get more into this later on, but if you see a case like this, in fact, we had one earlier, remember, with Symbol Lab, what was it? It was x squared minus 7. The very first example that I threw out there. Okay. Oh, x squared minus 3x plus 7. I didn't mention it at the time, but if you look at this graph very carefully, you'll notice something very important. Here it is. Oh, wait a minute. That's not the same one, is it? Oh, you know why? Because I just remember when you do this, you have to hit the go button first. Otherwise, it thinks we're looking at the old example. Okay, here it is, graph. Look, oh, it never quite reaches the horizontal axis. So this one has imaginary solutions. In fact, it may have calculated them for us. No, it doesn't seem to have. Okay, but yes, in this case, you would end up, if you try to plug these numbers into the quadratic formula, you'll end up with imaginary numbers. Okay. Not that you can't have imaginary numbers, but we're going to try to save that for another chapter. For now, let's assume that we're only going to have real solutions. Okay. Okay. Now we're going to get back into our discussion about functions. We're going to introduce a special type of function, the so-called one-to-one function. What is that all about? Okay, well, this means a normal function assigns a unique value to each element in the domain. In other words, let's see if we can fit this in here. We've already seen that this would actually count as a function, because even though both of these numbers are associated with 5, each value of x is associated with a single value of y. Now, a one-to-one function means that we can't have this. So in other words, one-to-one would require that each of these go to a unique value of y. Okay, so in other words, the one on the left is a function, but the one on the right, we call it a one-to-one because each of these x's goes to a unique y. There is, in other words, none of the y's are associated with more than one x. So what would be a good example of this? All right, well, let's try this. Birthdays. We've already seen that birthdays can look like the one on the left. Okay, let's throw in this example here. So imagine we're dealing with this very simple case. There's 2 people in the family, and just by coincidence, they were both born on January 1st. This is a function because John and Mary each has one and only one birthday. But this is not a one-to-one function because more than one person has the same birthday. But what if we're not looking at their birthdays, but how about their social security numbers? Should we have a situation where John and Mary can have the same social security number? No, we do not like that at all. So when it comes to social security numbers, everybody had better have a different one. So again, they're both functions. The one on the right has this extra special property. It's called one-to-one because it means that you cannot have each element of the range, which remember is on the right. Each element of the range is associated with only one element of the domain. Okay. So that's the difference between the two cases. Now, you may say, well, what's the big deal? No, you'll see later on that this can be a very helpful property of a function. It will help us solve certain types of problems if the function is one-to-one. Okay. Now, how would you see this on a traditional XY coordinate system? Let me show you how that would work. Let's say this is the one we had before. Y equals x squared minus x minus 12. So if you notice, two different x's are associated with y, 0. So therefore, this is a function, but not a one-to-one function. Because if you actually, the way you can imagine this is if you drew a line across this, let's say from here to here, the line touches two different values. This is sometimes called the horizontal line test. And in this case, the function fails the horizontal line test in the sense that there are 2 points associated with the same value of x. I'm sorry, they're 2 x's, but the same y. So that tells me this fails the test, is not one-to-one. On the other hand, though, what if we had something like this? All right, I'll get it, don't worry. No. I'm trying to, yeah, all right. So you can see here, each x is associated with exactly one y, and that's it. And you can tell because if you drew horizontal lines across, they would never touch the function twice. Okay, so this is a one-to-one function, whereas this one is not. All right. Okay. All right. So now let's see. Ooh, what time is it? Ooh, it's getting late here. So I did say before, this is a very, 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 very long class. So we have to have a break. A fairly, and I don't mean just like 2 minutes. I mean, enough time to actually get something to nibble on. Since you're right in your homes, that should be very quick. But why don't we'll stop right here for about, let's say 15 minutes. That should give you plenty of time to get something to eat. I'm sure you're starving by now. I'm sure you need some refreshments. We'll give it about 15 minutes or so. And when we get back, we'll carry on for a while. We don't have to stay the whole time today since it's the first class, and I'm sure your heads are reeling already. But what we'll do is we'll carry on for a bit, and then what I'll have you do is read through these slides between now and next week, and maybe even take a look at some of these problem sets on Moodle, just to get ready. You know, in other words, just to let's see, where's Moodle?
Can I ask a question?
Yes, go ahead.
Wait, is the slide gonna be shared with us or no?
Oh, it's already on Moodle. In fact,
Oh.
here's all the more reason. Let's go back and visit it for a second. If you go to Moodle, well, you know, two things will actually be shared with you. You see that what I did here was I put the actual slides with, oh, that's the wrong one, sorry. Pre-calc. The actual slide is right here, but when we're done, you notice I've written quite a bit on here. I will put this in here as well. I'll give it a slightly different name, like chapter 1 with handwritten notes or something like that. So this way you have the original PowerPoint slides with no writing on them, and you'll have all of this good stuff in here as well. Okay, so in other words, we don't want to lose this. In fact, this is when it actually pays to be online, because in the classroom, this would all get erased. Here, I've got a copy of it. And so I will save this and post it when we're done. So you'll have both of them to look at. And also, let's see what's in this practice problem set number 1. Ooh, see, already you can do number 1. So between now and next week, what you should do is read these notes, but also take a crack at this chapter 1 problem set number 1. Let's see what's in number 2. Oh, we haven't really done this yet. So no, never mind number 2. I mean, we might do some of this later on, but so we'll all right. So when we get to the end, we'll discuss this again. But so the point of this is that, you know, basically what today is all about is, of course, learning what's going on in this class, but also reviewing a lot of important concepts, getting your memories back up to speed, you know, because I'm sure a lot of this is coming back in a big flood. And, you know, you may have seen a lot of this before, but it's probably been a while. So, and refamiliarizing ourselves with math itself, and also just getting back into the habit of studying, which you know, let's face it, during the summer, you kind of get away from that a little. And so, yeah, what we'll do is next week, obviously we'll continue with this material, but we'll do this. We'll agree to go over the first chapter, the chapter problem set number 1, because you already can do this. And then as we go along, we'll continue to do new chapters and new problem sets. And then I don't remember how many chapters we have to cover to get to the first test, but it's going to be a good long time. I mean, easily it'll be in sometime in October. Today's only the first day of September, so don't worry about exams just yet, but do keep up with the material. If you don't remember, or if you just haven't seen this before, go through it. And then next time what we'll do is, when we start at the beginning, we'll go over any questions you might have. Like you might realize you don't understand something or other, or you want to go over it again, and that's good. We'll do that. And then when everybody's happy, then we'll dive back into the new material. Okay, so I don't want to just like blow through this stuff. And, you know, we have to cover a lot of material, but I do want to give you time to ask questions, and you'll have a whole week, every week, of course, because it's a weekly class, to review the notes. And if in between sessions you have other questions, you can send them to me by email. And we'll go over those by email. But when we're actually in the classroom, you can ask whatever questions you want. Okay. So anyway,
I got another question.
okay, go ahead.
At my other college, I'm a transfer student. At my other college, there was like a thing where it's called a math center where like you can get free tutoring, you know,
Oh,
so
I
it's a
think
walk-in.
we have that too. Yes.
Okay, I just want to make sure. I just want to make sure. Do you know which building it is it?
I don't know the details. You might have to call the math department, whoever's in charge, and ask them about it. I know that it exists. I just don't know any, you know why? Because I haven't actually, believe it or not, I haven't been on that campus in almost 2 years because of the COVID. And so I'm probably not the best person to ask. I would get a hold of somebody in the math department or the secretary of the math department and just say, could you tell me the details about the math center? Because I know they have one.
Thank you.
Okay, so yeah, check that out. And by the way, let us know next week what you find out, because there are other people in the class, I'm sure, would like to take advantage of that as well. Okay, so, all right. Anyway, so let's knock it off. Like I said, I'm sure you're ravenous by now, both physically and mentally. And you know, your brain needs glucose to stimulate itself and you know, process all this great information. So we'll stop for a bit. Let's come back around 10:05. Let's make it 10:05. Fully charged and ready to go. And then we'll carry on for a while, and then we'll take it from there. All right. So see you all in a bit. All right. All right, I guess we'll carry on from here. We'll go a little further. And then again, like I said, when we're done next week, for next week, you should read these slides and work on the first problem set. And then, of course, as we go along, we'll get more deeply into the material, but, today is a good introduction to what the course is all about and a good way to get back into the swing of things and review all of your math skills. And so anyway, let's see what's next. Yes, the horizontal line test. We've already kind of talked about that. The horizontal line test basically means that if you can draw a line through a function, like let's say this one, and the line touches more than one point, that means while this may be a function, it is not a one-to-one function. It's kind of an easy way to make sure that a function is one-to-one. So something like this is a linear function. When you have the highest power of x equal to 1, this type of function is known as a linear function. And that's partially, well, because let's face it, if it can be expressed as a straight line, you can see the word line hiding in the word linear. It is simply a straight line. And if you were to draw any horizontal line through here, it would only touch at exactly one point. Now we also have the vertical line test. So remember, the horizontal line test helps us identify if a function is one-to-one. On the other hand, we have the vertical line test rather. The vertical line test is a little bit different because this is used to identify if a relation is a function or not. Okay, so in other words, if you have something like this, let's say I have this bizarre relation that looks like this. A sideways parabola, basically. Now here you can see there's a problem because when x equals, let's say 1, this is associated with both, let's say 1, -3 and 1, 5. And as we've already seen, if there's an x that's associated with more than one y, that means this is not a function. Oh, I did not know such a thing existed. Closed captioning, huh? How did that happen? Did anybody in the class hit a button that made that? That's a very good idea. I like that. Look at this. It's actually repeating what I'm saying. I didn't do that. Does anyone in the class know what just happened? I'm just beyond surprised. No, I figured maybe there was a button on your screen and you touched it or something, and really? Well, anyway, let's just carry on. And so, yes, so this is not a function, as you can plainly see. And you can see because, again, really, okay, so there is an option, but how does that work? I wanted to know that somebody asked me about it yesterday and I didn't know what to tell them. How exactly does that work? Where did you see that option? I don't see it.
The option for a live transcript,
Yeah, where is it?
it's right next to the record button. For us, at least.
Oh.
Yeah.
That's kind of funny. Shouldn't it be on mine too? Oh, wait, there it is. Oh, no, I never noticed that before. Huh. Okay, and not only that, but it gives me a chance. I'm going to hide the subtitle because it's very distracting. But I interpret this to mean that the video itself will have titles. Wow, I am so glad. I mentioned this earlier in the beginning that I am not Mr. Technology. So anytime you stumble onto something like this, you can very much feel free to let me know because I will never find this on my own. I can tell you that much. Well, now that's good, because like I said, somebody in my class yesterday asked about this, and I really did not know if this was even doable. So that's pretty impressive. All right, great. Well, that mystery's been resolved. Beautiful. Okay. Anyway, so this is not a function, and we already know why, but now here's what the vertical line test is basically saying. If I drew a line through these points, you can see that because it will touch two different points on this curve, that means it fails the vertical line function, a test rather. And therefore, this is not a function. Okay, so the horizontal, remember the horizontal line test only helps us identify whether a function is one-to-one. The vertical line test is designed to tell us if it's a function in the first place. All right, now we're going to start looking at some different kinds of functions. We kind of alluded to a couple of them already, but we want to go back and revisit some of the functions that you've seen before and basically show how they are identified. So there's actually a long list here, many of which you're already familiar with. For example, the constant function, the identity function, and this absolute value, which you might recall, is what it essentially does is it gets rid of the negative sign in front of a number. Then we also have quadratic, which we've already talked about. We have the cubic function, we have reciprocal, reciprocal squared, square root, and cube root. So these are all functions we'll encounter many times. So we want to understand their properties right now before we see them again. Okay, so, and by the way, in all these cases, you should be able to identify them both by the way they're written algebraically and their graphs. So here's a perfect example, a constant function. What this means is that no matter what x is, y is equal to c. What does that look like? And c is any real number. So let's say I chose 5 as my constant. It's a horizontal line. That's all it is. It literally is just a horizontal line. It goes out obviously forever to the positive and negative infinity. It's just a flat line. By the way, here's an interesting question. What is the slope of this line? Now, we haven't revisited the concept of slopes yet. We might as well do it now. The slope of any function is delta y over delta x, which means the change in y over the change in x. Or you might have been taught this as the rise over the run. So let's pick two random points. Here's the point 1, 5, and here's the point 2, 5. So think of this as x1, y1. Think of this as x2, y2. So the slope can be written as y2 minus y1 over x2 minus x1, which means 5 minus 5 over 2 minus 1, which is simply 0. All right, so in other words, you can tell this is a constant function because the slope is 0, or think of it as the line being flat. It never changes, okay? So that is a very special case. It is referred to as a constant function. All right. Yes, go ahead, Fernando.
Could I ask why, when you're writing out the y2, y1 over x2 minus x1, could I ask why did you subtract it? Or
Because
would it like subtract
it's
it?
the change, because it's meant to represent the change, the difference. In other words, what you're trying to figure out is how much does y change given the amount that x changes. And so we subtract because we're trying to figure out if it's going up or down.
Oh, okay. So it'll always be subtracting, right?
Yes,
Or,
this one means yes. When you see that delta sign, it means you subtract.
all right, thank you.
It's like if you're trying to figure out what is the change in the balance in your checking account. You're going to look at what it is now versus last week, and hopefully it didn't go down. But yeah, that's what it means. Huh. I'm hearing an alarm going off outside my window. I want to make sure it's not my car. Okay, it wasn't mine. Okay, good. Very good. All right. Now the identity function simply means that y always equals x. Okay, that's it. So it's easy to see what this looks like. It's just a heart of, it's vertical. Well, no, it's a positively sloped line that goes to the origin. Okay, now how can you tell? For example, we have the point 22, 33, 44. Down here we have -2, -2. So in other words, you just go straight to the origin. This is called the origin, if you've forgotten. And the slope is 1. How can you tell? All right, let's check it out. Let me just randomly pick these 2 points. Okay. I'll call this one x1, y1, and x2, y2. So we're going to have 3 minus 2 over 3 minus 2. And so the slope is +1. Okay. It's like, imagine if you had 2 twins and you wanted to know, given the age of one, what's the age of the other twin? It's the same. It's always the same. Now, absolute value. Now, remember how this works. It means that f of x equals 2 possibilities. It equals the x if x is positive or 0. It equals -x if x is negative. This is the formal way of writing it. But it just means, and for all practical purposes, what it means is you're eliminating the negative sign if there is one. So you're only interested in the magnitude of x, not the sign. And for real world applications, there are many cases where we don't really need the negative. So we just basically discard it. It's like, if you remember from high school chemistry, the pH values that determine if a liquid is an acid or a base, those are actually negative numbers, but we just usually ignore them. So those are actually, if you want to be technical, those are absolute values. What does this thing look like? Well, it's pretty interesting. Oh, look at that. Yes, it's a big V. And not only that, but if you notice, it never goes down below 0. It can't. Okay, in other words, it starts at the origin, and then on either side, we have, for example, when x is 1, y is 1. Over here, when x is -1, y is also 1. So within this range, the slope is 1. On this side of the fence, the slope is actually -1. You can tell because it's going downhill. I guess you can think of it as downhill, but still at a rate of 1 to 1. Now, this function would fail the horizontal line test. In other words, I could take a horizontal line and read it, or put it right through here, and you can see it touches 2 different points. So therefore, I will conclude from this fails the horizontal line test. And therefore it is, although it's a function, is not a 1-to-1 function. Okay. Which you can tell just by looking at it. Now, the next one, which we've been already talking about, the quadratic function. How do you know that it's quadratic? Because it has x squared in it. Okay, that's all you need. So the general form looks like this, and the only restriction here is that a cannot be 0. The others can be anything, but a cannot be 0. Otherwise, if a is 0, it just ends up being a linear function. The a squared, x squared would drop out. So the only restriction is that a must not be 0. And of course, we already know that the graph is a parabola. Now, by the way, a parabola can have two basic shapes. It can look like this, but you know what? You might remember that it can also look like this. And that depends on the sign of A. When A is negative, it's like an upside down bowl. When A is positive, it's like a normal bowl, I guess. Okay, so here's an example, x squared minus 2x minus 15. I went ahead and graphed this in Excel, but you can certainly feel free to look at it in Symbolab. And this is what it looks like. And you can see if we were trying to find the solutions, they would be here and here. In fact, I might as well put them in here. Okay. And once again, this is not 1-to-1. Fails the horizontal line test. All right, now here's the next step up from this, the so-called cubic function, which contains x cubed. Wow, now that's a complicated function. Okay, so that's what, and again, you must make sure that a is not 0. Now the cube, this, depending on the relationship between these other variables, there's a few different shapes that it can take. Let's see, on the next slide, I've got what this one looks like, but maybe we should go into Symbolab and try some other ones. And so for this particular case, it has a very strange curve to it. Oh, look at that. Interesting. And if you notice, it is 1-to-1. Now, the x is positive. Now, if you look at these, all these are positive except for the constant. And let's see, let's try another one or two because they can get very strange, these cubic functions. Let me make up a couple more. Let's see now. First, this is x cubed. Plus 2x squared plus 5x minus 8 . Yes. So yeah, it looks like this. It's sort of now the thing is about the symbol lab is if you notice they've got large numbers on the axes. Like here, or a small rather, sorry. Here I've got it up to 250. So the shape looks a little different because the um I've got different values on the axes, but let's just do something. Let's try to change some of these signs just to see how it affects the result. Now, what a difference that made. Look at that. I changed the x cubed to negative, and now look, all of a sudden, it crosses the axis 3 times. Okay, so it has 3 solutions. Interesting. So, so these cubic equations can have up to 3 different solutions, not always, but up to 3, because of that x cubed term. Now, we're not going to cover this case, but let's just, for the fun of it, let's see what the graph looks like if we include x to the 4th power. Oh boy, that could be interesting. Oh, it's not nearly as interesting as I wanted it to be. You know what? I bet it's because we don't have enough negatives. But the idea here is that potentially it could cross the axis up to 4 times because there's an x to the 4th term. No, oh, I'm so let down here. I wanted it to be very complicated and elaborate looking. Oh, well, all right. Well, I don't know. It's getting a little weird, but yes, potentially could have up to 4. Now, let's take a look at the so-called reciprocal function. So in other words, y is just equal to 1 over x. And you can see right away, there's one thing we have to watch out for. X can never be equal to 0. Now, by the way, interestingly enough, I do have some interesting videos that we'll be watching throughout the course. I have found some very interesting material on YouTube. And one of the videos that we're going to see provides an extremely interesting discussion about why you're not allowed to divide by 0. It may not sound like the most exciting topic in the world, but I think you'll really like the way they've approached it. And it's also just visually fun to look at. It's a very well produced video. And so it turns out that if we allow x numbers to be divided by 0, then every number in the real number system would actually equal all the other numbers in the real number system. So that's something we don't want to see. So, but yes, just be aware, something like this, we're not going to allow x to equal 0. And that's going to have an important impact on the graph. Let's see what this thing looks like. All right, now again, Excel doesn't always do the best job with these graphs. I'd like to show this to you in Symbolab so you can get a better feel for what this is all about. There we go. Now that's a graph. Now, if you look at it very carefully, you'll notice that the graph never quite touches either the horizontal or the vertical axis. Those will never end up on the graph. There's a special name for these. In this particular case, the x and y axes have a very special name. They're called asymptotes. Okay, let me draw that into the slides real fast. Okay, so in other words, and it's very hard to do this properly, but I'm going to try. Yeah, that's tough. Well, what I'm trying to indicate is that no matter how far out X and Y go, the, the graph will never touch the X and Y axes. So therefore, this line, this axis is referred to as the vertical asymptote. It's called asymptote. This is simply the line that the function is approaching. And this becomes the horizontal asymptote, it's called. Okay. And so it's just a reminder to you that the function will never touch either axis. And you can see why. X can never be 0. So therefore, that's left out. But also, no matter what number you throw in here for X, Y will never be 0. That's why this is happening. Now, most functions don't have an asymptote, but some of them, the more bizarre ones, often do. All right, cool. So, by the way, and then what we also will say here is that where the function is not defined, we have what are called discontinuities. In other words, these are points where it does not exist. So you'll see that word again and again, discontinuities. Now, the next one is not just the regular reciprocal, it's the reciprocal of X squared. Okay, so now again, I'm going to show you what it looks like in Symbolab. The Excel graph isn't that great. But you're going to see it'll have some similar properties, except, all right, well, we'll see. All right, here we go. Ooh, now, first of all, you'll notice that once again, we have two asymptotes, the vertical axis and the horizontal axis. But on top of that, the function never appears in the third or the fourth quadrants. Because X is squared, it can never be negative. So you have an even more interesting function, two asymptotes, and the function is undefined in the third and fourth quadrants. Ah. Okay. So yeah. So the horizontal axis asymptote is the x-axis. The vertical asymptote is the y-axis. And then we also have undefined in quadrants 3 and 4. Okay, what about the square root? Now, remember, the XY coordinate system cannot show imaginary numbers. It can only show real numbers. So what that means then is that we will not allow X cannot be negative. Okay, so what does this thing look like? So it's restricted exclusively to the first quadrant, and it has sort of a curve to it. And again, I'd like to show you what this looks like in Symbolab because it's a little bit easier to follow. There it is. Yeah, it's a nice curve. It starts at 0, works its way up, but it increases at a progressively decreasing rate, if you notice. Okay, so it's exclusively limited to the first quadrant. There's no asymptote, by the way, but it is not defined in the second, third, and fourth quadrants, and it just basically increases at a decreasing rate. And you can see why. For example, this would be 4, 2, and this would be 9, 3, and you can see that the slope. Oh, that's another thing I almost forgot to mention. The slope is not a constant. Unlike this, we had one that it was a straight line. Here, the slope is not a constant. It gets flatter. In fact, the slope decreases as x increases. Okay. Beautiful. Now, here's another interesting one, the cube root function. Now, this one is interesting. I'll tell you why, because you can take the cube root of a negative number. Okay, it is not imaginary. For example, the cube root of -8 is just -2. So this is a little bit different. And so that means we do not have to restrict the function to a particular quadrant. And yet it does have this nice curvy look to it, which, yeah, I mean, again, it's a little bit awkward in Excel. So let's go to Symbolab. Yeah, it's kind of weird. It's curves up slowly, then it sort of hits 0 and then smooths out and it basically flips over. It's a very odd little function. Oh, you know what I just realized too? It's only going to appear in the first and the third quadrants, not the second and the fourth. Okay, and there's no asymptotes. Okay, so. Very good. All right, so now we have this idea about the properties of these very important functions. That will come in handy as we go along, but now we're going to move into a slightly different area. What we're going to do is try to identify for any given function, what is the domain? Now remember what the domain means. The domain represents the x values that can be substituted into a function. Now remember before, when I said that for something like this, x cannot equal 0. That means the domain of this function is all real numbers except 0. And that's because 0 would lead to division by 0. So it's not allowed. The function cannot have 0 substituted into it. So any real numbers that cause a function to become undefined are not included in the domain. In fact, if you go back to Symbolab, it actually has this information here. if we go back and put in 1 over x, and we graph, well, we can graph it again, but somewhere up here, they mention the asymptotes, but also, yeah, here it is, the domain. They're going to do this for you. Look how nice that is. So there's 2 equivalent ways of writing the domain. So first they wrote x is negative or x is positive, meaning that it's not 0, or they used interval notation. Well, let's take a look at this. All real numbers except 0. This can be written in 2 equivalent ways. So in Symbolab, they're showing us that you can put x is strictly negative or strictly positive. But to use interval notation, I'll do this one by hand. What we're going to use is parentheses, actually. What is this all about? Well, obviously, this is infinity. And, you know, you put a negative, that's negative infinity. U represents union, which means you're combining these 2 sets. Now, I just want to remind you, when we use this notation, this means that interval, actually, let me put this on the next slide. Just a quick reminder. Okay, just a quick reminder about how this notation works. If I put something like this, this means all values between A and B, not including A or B. Okay, so it's everything in between except, but not A and B themselves. If I put a square bracket here, this means all values between A and B, not including B. In other words, this one means I do have A in there. But on the other hand, this means all values between A and B, not including A. And then finally, if I have both square brackets, that's all values between A and B, including both A and B. Okay, so in other words, the square bracket means yes, that counts. The round or bracket or parenthesis means no. Okay. Now, if you notice carefully, let me just do one thing here. Before I forget. It's taking a while. This is a big file. There we go. Yes, so. Oh God, now I forgot what I was going to do. Oh, I know what I was going to say. based on this notation, we always use the round brackets or parentheses to indicate positive or negative infinity. Okay, I just want to mention that. If you notice, if you look at it here, so here, what this means is that we're going from negative infinity up to, but not including 0. And then on the right-hand side, we're starting not quite at 0, so whatever comes next, all the way up to positive infinity. So this is sort of a roundabout way of saying everything but 0. Okay, so that's why we have the round brackets here. And the union sign means combine these two. So that's the domain for that particular case. But, you know, in many cases, finding the domain is a little bit less straightforward because we have to avoid, like we said, division by 0, or in many cases, we have to avoid having negative square roots because we're trying to focus on real numbers. Okay, now let's get this out of the way. So how do we do this in general? We identify what values can go into the function, identify restrictions, and then in this book, at least, they prefer to use the interval notation. It doesn't really matter, but the book likes the interval notation, so we'll stick with that. Now, like here, for example, what is the domain of this function? So let's look at it in Symbol Lab. Now, what we're looking for is breaks in the curve. There don't seem to be any. In other words, if you look along the horizontal axis, is there any point where x does not seem to be part of this function? And the answer is no. Okay, there's no asymptotes, there's no discontinuities. So in a case like this, the domain is all the real numbers. Every value of x is valid. There's no value of x that can't be substituted into this function. So therefore, in this simple case, the domain is just the range between negative and positive infinity. And for many functions, that's exactly the case. All right, now let's try a slightly trickier one. Now, this one we already know. We've already seen it. Anything goes here except 0. In fact, let's go back to Symbol Lab and remind ourselves what this looks like. So you notice, oh, now remember, we're only interested in which x's cannot be substituted into this function. The range is the y's. Okay, the x is the domain. And so the only x that doesn't seem to fit here is 0, right here. The vertical axis is the line where x equals 0. So that means everything else can go into this function. And as we've already seen using the notation, the interval notation, that means you're including everything except 0. All right. Now here's an interesting one. And it should be fairly clear what's going on. What about this function? Is there a value of x that is not permitted? What do you think?
5.
5, exactly, because that would lead to division by 0. So let's take a look at it in Symbol Lab. All right, so let's see, where are we? Oh, here we go. Okay, so here, as far as the vertical asymptote is concerned, it's not 0 this time, it's 5. Okay, in other words, like you said, 5 would lead to division by 0. Also, if you notice, the horizontal asymptote is also not at 0 any longer. Looks like it's also 5. No, it's not. It can't be because 5 is up here. It looks like it's 1. But anyway, so what we do know then is that we can substitute anything we want into this function except for 5. So therefore, the domain is the interval -infinity up to but not including 5 with 5 up to infinity not including 5. All right, so those are the easy ones. Here's a good one. Let's try this one. What values of x do you think would not work in this function? No, 3 is okay because that would give us a square root of 0. But if we have anything below 3, let's say it's 2, you're going to get a negative square root, which is imaginary. So remember here, we're focused only on real numbers. So the domain is all values from 3 up to infinity, including the 3. So this time we're going to use the square brackets. All right, because 3 is included. Anything below that is no good because it'll give us a negative square root and therefore an imaginary number. So again, just for the fun of it, let's take a look at this in Symbolab, which is rapidly becoming our favorite program. The Symbolab. Yes, you can see it's simple. It starts where x equals 3, and it goes from there, but there's no value of x to the left of that. It's simply not defined. Therefore, the domain is simply everything from 3 up to infinity, including the 3. All right. What about the range? We also want to take into account the range. So let's start with some of the basic functions we've looked at. Now, the constant function is pretty straightforward. But, well, even then, it has some interesting features. Let's try 5. It's just a flat line. Now, so what that means is that all values of x are valid. The domain is the entire real number line, but the range, meaning the values of y, is just 5. So we write it as the interval 5 to 5, basically. It's just 5. That's the end of the story. How about the identity function, y equals x? We did that before. Let's revisit that. Well, now here's what we have to ask ourselves. Are there any values of x that do not work? No. Are there any values of y that we will not ever see on this graph? The answer is no. It covers the real number. In other words, the function will cover both the entire vertical and horizontal axis. Therefore, the domain and range are simply all real numbers. Now, here's an interesting one, the square absolute value. So let's look at it again in Symbolab. All right, so you can see that all x's are good, but the y, there are no negative y's. Okay, there can be a 0 y, but there can't be any negative y's. So therefore, while the domain is all the real numbers, the range is everything from 0 up to infinity, including 0. That's why we have the square bracket. Very good. Okay, how about the quadratic function? It doesn't matter which one it is, whether it's an upwards facing parabola or downward facing. In fact, let's go out of our way to find a downward sloping one, just for the fun of it. Now, in principle, in this particular case, the y value will never go above, what is this, 5? Looks like it's negative 3 point something. But in general, for any function that you choose, there's no restrictions on x or y. So we'll call these all the real numbers. Now, for some specific cases, it might not work that way, but just in general, for all quadratic functions, there's no restrictions on the domain or the range. Oops. All right, now the same thing is true of the cubic functions. And there's no restrictions on the range or domain. Okay. Now, the next one is the reciprocal function. We've already seen this one. We know that there are gaps in there. Okay, so let's quickly remind ourselves. Let's go back here. Ah, there we go. So you can see that we have two asymptotes. Okay, so therefore, and it says it up here somewhere too, x equals 0, y equals 0 are asymptotes. They are disallowed, which means the range, the y's I mean, cannot include a 0. The domain, the x's cannot include a 0. So in both cases, the range and the domain are both the entire real number line except for the 0. And so that's why, and of course we saw earlier that this is how we write this. This is meant to indicate the entire real number line except for 0. All right, let's see. How many more of these are there? Just a few. How about this one? Reciprocal of the square function. Oh, that's right. Let's try that one. So remember, this is the one where we still have a vertical asymptote. X cannot equal 0, but if you notice, y cannot be negative. So, in other words, this is only restricted to the first and second quadrants. So how do we express that? Well, the domain clearly means all values except 0, but the range, the zeros, the y's, are from 0 to infinity. But you notice we do not include 0 because that horizontal axis is an asymptote. And it shows it right up here. There it is. The vertical asymptote is x equals 0. The horizontal is y equals 0. So we cannot have a 0 in either the range of the domain, but in the domain, we can have all real numbers except 0. In the range, we cannot have any negatives. We have to have strictly positive numbers. All right, now the next one we considered was the square root function. Let's take a quick look at Symbolab. This is the one, remember, where it starts at 0, x starts at 0, works its way up to the positive values. So neither x nor y can be negative, although they can both be 0. And so therefore, that means in both cases, the domain and range is everything from 0 up to infinity, including the 0. Okay, we can have zeros here. All right, and then the cube root function. Let's check that one out. That's this weird thing. So what restrictions are there the cube root function? There aren't any. There's no value of x that's not possible, and there's no value of y that's not possible. So in this case, we've got the entire real number line. All right. I'll tell you what, it's 11 o'clock. You know, this is the first day of class and we've gotten a lot done. So why don't we stop here? I know it's a little early, but we need to get back into the swing of things. And I'm sure that everybody's getting a little weary of this because it's been a while. So why don't we stop here, and what you will agree to do is between now and next week, take a look at chapter 1. Actually, next week we'll start chapter 2, so I'll post that as well. But in the meantime, I'd like you to take a peek. Let's look at these problem sets again. I'm not so sure that you're, let me just see. Number 1, you can do for sure. Yeah, you know how to do those. Let's see if we've gotten through number 2 yet. Not exactly. No, all right, so we'll hang on to number 2 for next week. All right, or the week after. All right, so in other words, here's what you're gonna do. Take a look at just review or refresh yourself on the notes for chapter 1 and the introduction to 2 as well, because we should get to that next week. And also work on these practice problems so we can go over them next time. I won't be collecting them. They're not being graded. It's just for your practice, okay? And then the following week, we'll of course do 2 and 3 in the classroom. All right, so, and you know, you might as well look at the syllabus too while you're at it. All right. Now, are there any last minute questions? Yes, go ahead.
Just wondering. So then that means we won't be going over any of like the questions of like the problem sets, like, or that'll just be on our own to figure out.
No, we're going to go over them. Absolutely. No, first thing we're going to do on next week is open this up, and I'm going to have you tell me what your answers are. Okay. In other words, like we'll start right here with this one. There's 8 questions, and I'm going to ask you what you got for these, and then we'll go over them. And then I will send out the solutions. I'll post the solutions on Moodle, and then we'll carry on with the new content. So I'm not going to collect these from you. I'm not going to grade them, but I will want to find out how you did on them. And I also will, of course, show you how to get the correct answers.
All right.
All right. So it's
All right,
all for practice, all practice.
All right. Thank you.
All right.
All right.
Anybody else?
Wait, I have an iPad, and I was wondering, can I use my like my Apple Pencil, to write over it, like my electronic pencil, to write over the homework, or do I have to specifically type it out?
Oh, you can definitely do that. I believe you can.
I
I'm
know how
not
to
that
do it. Like,
familiar. Yeah, I'm not that familiar with Mac products, but from what I understand, you should be able to do that. And if that's how you want to do it, that's fine with me. In fact,
I just want to make sure, because some teachers prefer me just to type it out, and I just want to get clarification with you before.
No,
you don't
not
take-
this stuff. No, if this was an English class, I might say, just go ahead and type it. But since it's math, typing, believe me, typing math is not easy.
No, it's a pain.
So yeah, if you can do that, that's fine with me.
And okay, great, that works for me. Thank you, I appreciate it.
Okay, sure. Anyone else? All right. Well, then if you think of a question later on, just send me an email. But other than that, I hope you are not too terrified after today. But so we'll go through all of this multiple times. Don't you worry. We're not going to rush through anything. And to make sure that when we get to the first test, everybody's completely ready. And but in the meantime, you can recuperate until next Wednesday, and I'll see you then. Okay.
Thank you.
Bye.
Thank you, sir. Have a good day. Bye, everyone. Take care.
Bye.